Okay, so we are now going to consider global static instruction scheduling techniques. In contrast to local static instruction scheduling, global static instruction scheduling considers multiple basic blocks. And the first technique we are going to review is called loop unrolling. So the first step, actually what loop unrolling means is that we create a larger basic block by actually considering multiple loop iterations and forming one larger basic block by actually repeating the code in multiple iterations. So here we consider loop unrolling when we unroll the loop executing 2 iterations in one code sequence. So that is what is shown to the left, and there you can see that we actually replicate the basic computation of each iteration twice. And we do one other step too, and that is to adjust the displacement in front of the address registers R1 and R2. So in the second iteration we actually use 4 instead of 0, because we haven't the address registers R1 and R2 will be incremented further down in the unroll loop iteration. You can see we add 8. Okay, that's the first step, but we have a complication here, and that is that we use actually reuse now the same registers in 2 iterations, and that is F0, F1 and F2. So we actually, in the second step in the process, we have to rename the floating point registers, and that is what is happening here. So in the first iteration we use the basic registers F0, F1 and F2, but in the second iteration we do renaming to use F3, F4 and F5. Okay. This transformation does not make things more efficient, but what we have created is now a larger basic block, so we will have more flexibility to do code motion, okay, to get to eliminate stall cycles caused by read after write dependencies. And so let's now look at how we can do code motion to get rid of all the stall cycles, and that is what is shown in the next diagram. And the basic trick here is actually to move all the loads to the top and all the stores to the bottom. That way we maximize the distance between dependent instructions. Okay, so the effect of that will be that we actually get rid of all the stall cycles, as you can see from the leftmost of the 2 columns to the right, which refers to the stall cycles of the basic pipeline. Now the last column actually refers to the super pipeline version, where we still see a few stall cycles here and there. So the effect of this on the execution time will be as follows. So if we count the total number of cycles for the 2 iterations, we end up with 14 clocks, which corresponds to 7 clocks per iteration of the original loop. That's great news. So the loop speed up, we had 15 clock cycles from the very beginning in the original loop, and now we only have 7, so we enjoy a speed up of 2.14. Now considering the super pipeline processor, again, second of the 2 columns with the stall cycles, then the total time will be a little bit counted in clocks, of course. There will be more clocks. It will be 17 clocks, corresponding to 8.5 clocks per iteration of the original loop. But now we can clock this pipeline twice as fast, so we can enjoy a clock frequency, a doubling of the clock frequency. So the speed up will in fact be 2 times 15 divided by 8.5, which is 3.52 in speed up. or 3.52 times faster than the original loop. So that's really great news. So loop unrolling seems to be a very effective technique to remove the stall cycles for dependent instructions, and the overall approach here is actually to create larger basic blocks. Actually, so let's look at also loop unrolling in the context of superscalar processors. And so here to the right, in fact, we have the optimized unroll loop, and now the objective is to try to execute 2 instructions per cycle, where one must be a floating point instruction and one is an integer instruction. The problem with this particular loop is that floating point operations are dominating. So there are very limited opportunities for actually executing a floating point operation in parallel with an integer operation. And you see the result of that schedule to the left. And the reason is the imbalance between the integer and the floating point instructions. Now, what are the limitations of loop unrolling? In fact, this could look to be too good to be true. Well, it works well if loop iterations are independent, and that's not unfortunately always the case. So here is an example of iterations that depend on each other. So here the basic computation is such that in order to compute the vector element I, it depends on a of I minus 5. So there is what is called a loop carried read after write dependency recurrence with a distance of 5 iterations. So that puts a limit on how much we can unroll this loop. It can also only be unrolled 4 times. In fact, this is a very general kind of problem. If we have loop carried dependencies, that will actually limit our possibilities to uncover instruction level parallelism, or by the way, any parallelism. But there are other more specific limitations, specifically inherent to loop unrolling. One is that it consumes more architecture registers for renaming. As you saw, we had to use up more registers to in fact as many times as the number of times the loop is unrolled. And of course it also leads to code expansion. Now the loop will take more space. Of course this is could especially be an issue for the instruction cache, which is quite limited in size, so it may actually increase the cache miss rate, and actually that way affect the performance adversely, in the worst case actually cancelling the improvements gained by better code scheduling. Okay, and it will also could also be an issue for the memory, that it takes up more memory space. This could be especially a problem for small embedded devices. And intrinsic to loop unrolling is that at compile time we have to know how many iterations are going to be executed, and that might not be known at compile time. We're now going to consider another global static scheduling technique, and that is known as software pipelining. So the approach in software pipelining is the similarity with loop unrolling is that is in its objective to actually increase the distance between dependent instructions, but the approach taken is differently. What we try to do here is actually to transform the original loop so that we create loop iterations in a different fashion, so as to increase the distance between dependent instructions. So we form new iterations by actually plucking, you could say, instructions from the original, from different iterations in the original loop. Okay, so here so if we look at the simple loop, since the add is a long latency operation, we want to pipeline the two loads and the add in one iteration, and then the store separately, because that will cause a lot of store cycles to show up. So in this diagram, what we see first of all is the columns actually correspond to the original iterations. So O underscore ITE1 is the first iteration, O underscore ITE2 is the second iteration, and so on and so forth. So for example, here we can immediately identify the four operations of the core computation, the two loads followed by a store, add, and followed by a store. So now we want to form a new iteration by actually looking horizontally. Okay, so here we form in the software pipeline loop in iteration 2. What we do is that we want to execute the store from the original iteration 2 plus the loads of and the add from the original iteration 3. So that will form a new iteration in the software pipeline loop. And a very important observation that is happens when we do this iteration, that is that independently, if we execute the original iterations one by one, or the software pipeline iterations one by one, we execute the same number of instructions and do the same job. And that's, of course, ultimately what is important. So here is actually the software pipeline loop, and I'm going to explain exactly what we did to end up with this. So as you can see, in the software pipeline loop, what we do is actually, as we did in the original loop, we do the loads and then we do the add. Okay, but what has been removed from this iteration is the store instruction, which actually caused a lot of headache. Okay, and what we so what we have added to the loop instead is the store operation of the previous iteration. Okay, and that is shown by actually using a displacement of -4 instead. Okay, then we of course do some code motion here. So we put the subtraction instruction of the loop index in between the loads and the add to increase the distance. Okay, so then we have gotten rid of all these dependencies. Now there is so this is the steady state. What will happen is that we execute these iterations, but in order to fill the pipeline and empty the pipeline, we have to also add what is called an epilogue, which fills the pipeline. And what is happening there is actually that we do the loads and the add for the absolutely first iteration, because the store on the first iteration will happen in the next iteration, as we saw. And concerning the epilogue, when we drain the pipeline, we will have to add the store for the last software pipeline iteration. Bottom line is that there will be no stores, and in contrast to loop unrolling, there will be no code expansion, and also, unlike loop unrolling, no register renaming. Well, what we can also do then is to combine loop unrolling with software pipelining, but then actually it turns out that we have to do software pipelining first and then apply loop unrolling, because the other way around would not make sense, because there are loop unrolling creates dependencies that would sorry, I said something wrong here. We would have to do loop unrolling first and then software pipelining, because software pipelining creates dependencies that will basically make loop unrolling ineffective. Okay, so what are the limits of the static pipelines? So strengths: hardware simplicity, clock rate advantage over complex designs. So what we have played with now is actually to move the job to the compiler. It's predictable, the static performance predictions are reliable. And the compiler has a global view, which is an advantage, so we can optimize loops, as we have seen with loop unrolling and software pipelining. There are power energy advantage, since we can go for very simple pipeline. There's a potential for being more power and energy efficient, and it's a good target for embedded systems. Now for the weaknesses, the problem to give the responsibility to the compiler to do code scheduling is that may show up to be, that may eventually turn out to be inefficient, because there are dynamic events which happen when we execute the code that will change the rule of the game, so to say, and those are cache misses and conditional branches, which will add new stall cycles that cannot that the compiler didn't assume, and it will freeze the processor on a miss, which cannot deal with latency tolerance. Okay, and of course the compiler's ability to have all the dynamic information available will limit its scope for doing a good job as far as code scheduling, for example with memory addresses. And there is no good solution for precise exceptions. Okay, so we will now consider dynamically scheduled pipelines next. But before we do that, let's look at the fourth quiz. So here we consider loop unrolling as transformation. We have the original loop to the left and then the unroll loop to the right. And the question is, in the unroll loop, which of the code transformations that are correct. There are some errors that I want you to identify. Before I go through the solutions, I would like you to stop the movie and think about it, and then I will present the correct answers. Okay, I will now present the correct answers. So as far as A, the load instruction actually that happens, which is the third instruction in the unroll loop to the right, should be, instead of having a displacement of 4, it should have a displacement of 0. And that is wrong. It should be actually as it is. It should be 4 because it refers to the second iteration. Okay. Moving on to B. The add immediate R1 R1 4 should be add immediate R1 R1 8. That is true because we have two loop iterations, so we have to add 8, otherwise it will not work. So that's correct. That was an error in the loop transformation. Moving on to C, store instruction F20 R1 should be F2 minus 8 R1, and that is also correct because we have moved the store instruction to after the add immediate, which added 8, so we have to compensate for that. So that's actually correct. And going to the last store instruction, instead of 0 R1 it should be -4, and that is also correct because this one is comes from the second iteration, but now we have again moved it ahead of R1, the add immediate to R1, which added 8, so now we have to subtract 4, so that's correct, to end up with pointing to 4. So that's correct.